So just like in our consideration of electric fields where we had continuous charge distributions, we must also account for this when we look at the potential. So previously we saw that we could have a sum of charges, and the potential due to a number of charges is just given as P of r is equal to 1 over 4 pi epsilon naught by the sum of I is equal to 1 to some number n qi over r minus r prime. Okay, and of course this is ri. Okay, so basically just add them all up. Now what happens if we have a continuous distribution? What's the potential due to that? Well, for continuous distribution we'll have our potential of r be equal to 1 over 4 pi epsilon naught. Now what we do is we take our integral over this charge distribution so that we get 1 over r minus r prime, and that is with respect to dq. Okay, so this is for a continuous charge distribution. And what about for a volume charge? Well, for a volume charge, we have V of r is equal to okay, now we'll consider that we have a charge density rho. So here we have rho of r prime all over r minus r prime, and here it's differential with regards to the volume, so it's d tau prime. Okay, remember we're using the prime here to signify we're integrating with respect to the source. Okay, so these are the potentials for localized charge distributions, and just to reflect a little bit, if we write down what the electric field is for our volume distribution, so the electric field for a volume distribution will be equal to 1 over 4 pi epsilon naught integral of rho r prime all over r minus r prime by r minus r prime divided by the magnitude and this is d tau prime. D tau prime okay, so what we can see is that there's the main difference between our potential and our electric field is for the potential we no longer have the unit vector that we have in the electric field situation. Okay, the other difference here is, and what I've forgotten here is, the electric field it's divided by r minus r prime to be squared. We also have this dependence on 1 over r squared compared to for the potential it's 1 over r. So let's do an example. What we're going to do is calculate the potential on the axis of a disk of radius r and surface charge density given by sigma. Okay, so let's draw this. Okay, so here's our disk. It's got a radius given by r, and it's got some surface charge density which is given by sigma. Now, in order to solve for the potential of the disk, what we're first going to do is we're going to divide the disk up into a number of rings. Okay, these rings are given by this blue line, and it's going to be at a distance r, or have a radius of r from the origin. Okay, I'm going to calculate the potential along the axis of a ring. Okay, let's say at some point given by P. Okay, and this is along the x-axis. So, here's your point P, this is some distance x. Okay, so just let's recount what our potential is given by. So the potential, which is V of R, is equal to 1 over 4 pi epsilon naught by Q over R minus R prime. So what's R and R prime here? So R prime here is X. Our origin is at the center of the disk. And so R, our field point, is given by X, and R prime for a ring is given by R. Okay, so this distance here from the ring down to the point P which is given by the square root of R squared plus X squared. Now, the ring is also going to have a certain thickness, which is going to be given by dr. And we're going to divide the charge up on this ring, and the charge in the ring is going to be given by dq. So our potential now is going to be V of R is equal to 1 over 4 pi epsilon naught by the integral of 1 over square root of R squared plus X squared dq. Okay, so we're integrating over all of that charge. So now what we simply get here is, just as for the potential of the ring, be 1 over 4 pi epsilon naught by Q, which is the total charge in the ring, divided by the square root of R squared plus X squared. Okay, so now that's the first part of solving the problem. Now what we must do is we're going to take this and then integrate over the complete disk. Now, since the area of our ring is only a part of the area of the complete disk, what we can write is this is going to be equal to dA, which is going to be equal to 2 pi r dr. So what this means for our charge is that our total charge on the ring, which we previously called Q, is now equal to sigma, which is the surface charge over the disk, by 2 pi r dr. So now what we must do is integrate what we had before between 0 and r. So the potential for the disk will be equal to 1 over 4 pi epsilon naught by the integral from 0 to big R of sigma, so sigma by 2 pi r divided by the square root of R squared plus X squared dr. So this is equal to 2 pi sigma over 4 pi epsilon naught, and we've got the integral of R over square root of R squared plus X squared dr. Okay, so now we just have to do is work out this integral. And this integral is going to have the form of the integral of u to the power of n du. Okay, because you can write the integral is r by the inverse square root of r squared plus x squared. Okay, so if we write this out now as v of r will be equal to 2 pi sigma over 4 pi epsilon naught by r into r squared plus x squared to the power of minus a half dr. And we solve this integral, and what we get is v of r will be equal to sigma over 2 epsilon naught by x squared plus r squared to the power of a half minus x. Okay, and that is our final answer. So what we did is we broke it up into different rings, and then we integrated over the surface of our disk in order to find the potential. So now, of course, if we wanted to find the electric field in the x direction, all we have to do is differentiate our potential with respect to x.